Happy Wednesday. So I got one person asked all of these questions, and then I got a couple more that asked questions on these two, 19 and 25. So I'm going to start with just 19 and 25, and if you're the person that asked about all of these in addition, maybe I'm hoping these two help a little bit. If they do or don't, just shoot me a message and let me know if you still want to see one or all of those. So the first one is number 19. That's the function, and the instructions are asking for the points of inflection. So points of inflection are points where we change from being concave up, let's say, to concave down. So right at that moment, it's concave up and concave down. That would be a point of inflection. So that's where the second derivative is 0 or undefined. So f prime of x, and I'm going to rewrite this as x times x plus 3 to the 1/2 power. So it'll be first times the derivative of the second, 1/2, x plus 3 to the negative 1/2, times the derivative of what's inside though, which is just 1, plus the second times the derivative of the first, which is just 1. So when I'm pulling out a GCF, I'm going to pull out x plus 3 to the negative 1/2 power. From here, I'll be left with 1/2 of x. And from here, I'll be left with, if I divide out x plus 3 to the 1/2 power, I'll be left with, to the negative 1/2 power. Dividing common bases, keep the same base, subtract your exponents, 1/2 minus negative 1/2 is 1. So that's going to clean up to x plus 3 to the negative 1/2 power, and then 3/2 x plus 3. That's 1/2 x plus 2/2 x, which is 3/2 x plus 3. So there's my first derivative. And then when I move on to my second derivative, again, I'm going to follow the product rule. So my first times the derivative of the second, which is 3/2, plus the second times the derivative of the first, which is 1/2 out in front. And then when I'm looking at these two, I'm going to factor out the smallest exponent. And that would be x plus 3 to the negative 3/2 power, which from this part, you know what, I can take out a 1/2 also. Because when I take a 1/2 out of this one, it's going to leave me with 3, and then x plus 3 to the, if I divide out x plus 3 to the negative 3/2, you divide common base, you subtract the exponent, so it'll be, if I'm dividing out x plus 3 to the negative 3/2, keep the same base of x plus 3, and do subtraction, negative 1/2 minus negative 3/2 is negative 1/2 plus 3/2, which is 2/2, which is to the first power, plus, when I take out the half from there, I lose that. I still have a negative sign, so it's actually going to be a minus. That whole thing got taken out, so it'll just be minus 3/2 x plus 3. So if I clean this up, I've got a 1/2. I'm going to bring my x plus 3 to the 3/2 to the bottom. This is going to be 3x plus 9 minus 3/2 x minus 3. So that's going to be 6/2 x minus 3/2 is still 3/2 x plus 6. So that's plus 6.5. 6.5, and 6.5 will be 13/2. And I think I'm going to clear complex fractions by multiplying by 2 over 2, which is going to give me 3x plus 13 over 2x plus 3 to the 3/2. Okay, so my critical points are the zeros and where it's not defined. So that'll be negative 13/3, which is the same as negative 4 1/3, and then negative 3. So I'm going to test my concavity inside and outside of all of this. So negative 5, for instance. If I plug in a negative 5, I'm going to get negative 15 plus 13, which is a negative on the top, over negative 5 plus 3 is negative 2. Negative 2 to the 3/2 power you can't do. So why not? So negative 5 plus 3 raised to the 3/2 power. The reason I think you can't do it is because when you half, you'd be square rooting it. So you can't do it. So this does not exist. We can't even talk about concavity there. Then if I plug in negative 4, I'm going to get negative 12 plus 13, which is a positive. Negative 4 plus 3 is negative 1. Negative 1, same thing. Can't even discuss it. And then negative 2, we'd get a negative 6 plus a 13, which would be a positive. Negative 2 plus 3 would be 1. 1 to the 3/2 power is 1. Point is, it's positive, so it's concave up. So let's kind of see what's going on here and why this is kind of tricky. X root x plus 3. So yeah, so if you go back to the original function, it doesn't even begin to exist until negative 3. So the function doesn't even actually exist over here. And then after it, it's concave up the entire time. So here it is, starting at negative 3, and it's concave up the entire time, which means there are no points of inflection on this one, which we see because there's no place where it goes from negative to positive or from positive to negative. So there's no points of inflection. It is just concave up for the duration of the domain which was x is greater than or equal to negative 3. So had I thought about that in advance, I would have realized it, but I still get to a point where I realize, oh, you can't even discuss the concavity doesn't exist down here. And the reason why concavity wouldn't exist, one of the reasons why it might not exist, is because the actual function itself does not exist. So let me just double check my answer to make sure I'm not telling you lies. So yeah, it says concave up from negative 3 to infinity. Positive means concave up. That's what we're seeing. There are no points of inflection. And then number 25. Same directions. Secant of x minus pi over 2, only on the interval from, lost my page, 0 to 4 pi. So this is really just the secant graph that's been shifted right pi over 2. So if I just get a quick visual, the cosine graph looks like this from 0 to 2 pi, and then 0 to 4 pi. The secant graph then therefore would be this, and we're shifting the whole thing to the right pi over 2. So actually, rather than shifting everything to the right pi over 2, I'm just going to move this back pi over 2. So you get the idea. So when is it concave up or down? Concave up, concave down, concave up, concave down. We see the point, but let's see how the work might be able to lead us to the same point. I don't believe there's going to be any points of inflection because the change in concavity is happening surrounding an asymptote. So it's not exactly a point of inflection. But anyway, let's jump into the algebraic way of looking at it. So the derivative of secant is secant tan. Times the derivative of what's inside, which is just 1. And then the second derivative is going to require the product rule. So your first times the derivative of the second, and the derivative of tangent is secant squared, times the derivative of what's inside, which is 1, plus your second times derivative of the first. Derivative of secant is secant tan, oops, x minus pi over 2. And I could write another tan, x minus, like, because the derivative of the second is secant tan. Rather than writing another tan, I'm just going to go square. So, and actually on this one, I should have just done a secant cubed. Secant times secant squared. I didn't realize at the time that that's just a secant cubed, and I can get rid of this one. Here we are. So now we can factor out a secant of x minus pi over 2, and I'm left with secant squared plus tangent squared. And then I want to see where this is 0 or undefined. So let me think about this. The secant of anything is never 0. Because that would be where the cosine is undefined. If the cosine is undefined, then the secant would be 0. And the cosine is never undefined. And if you just look at the basic secant visual, it never equals 0. And then we're just going to pretty much find where this, if you just are doing this part, we don't really even need to worry about this part, because if we're trying to look at where this equals 0 and it doesn't, and we try to look for where it's undefined, the places where this is undefined, which is just the first portion of the second derivative, are going to be the same as all of the places where the whole function was undefined. So secant graphs typically, let's see, I'm going to do this again. Secant graphs typically are undefined where the cosines are 0. So at pi over 2, 3 pi over 2. Okay, so cosine of theta equals 0 at odd pi over 2's. So that means the secant of theta equals undefined at odd pi's over 2. But every one of those odd pi's over 2 got shifted right pi over 2. So pi over 2 got shifted, 3 pi over 2 got shifted, 5 pi over 2 got shifted, and actually negative pi over 2 got shifted. To the right pi over 2 would put that at 0. To the right pi over 2 would put that at pi. To the right pi over 2 would put that at 2 pi. To the right pi over 2 would put that at 3 pi. So, and one more, 4 pi, because they want this on the interval from 0 to 4 pi. So all of these asymptotes that we saw here, 0, pi, 2 pi, 3 pi, 4 pi. So we are not dealing with any points of inflection. We are dealing with concave up from 0 to pi, and again from 2 pi to 3 pi. We're dealing with concave down from 0, pi, 2 pi, 3 pi, from pi to 2 pi, and 3 pi to 4 pi. It's easier there to just know and have faith in your graphing abilities than it is to do a sign chart here. I mean, I'm not even sure what that would look like, and I don't want to take myself down that path, because when you do your sign chart, you're just going to be testing in and around 0, pi, 2 pi, 3 pi, and 4 pi. And they're all going to be positive or negative based on this one only, because when you take a secant of something and square it, it'll be positive, plus tangent of something squared, it'll be positive. So it's all just going to come down to the sign of this one, which we can go back to the original visual to grab and not have to come up with all those secant values of things in the certain intervals. And not, we could do it, like we could test pi over 2, you plug it in, you'd get 0, the secant of 0, well, the cosine of 0 is 1, so the secant of 0 is also positive 1, so you'd know that that was positive, aka concave up, as we already know it is. You could plug in 3 pi over 2, subtract your, and do the whole thing, but to come up with the secant value, you have to come up with the cosine value, then reciprocate, and it's just a lot of drawn out steps. Whereas this, you can just look at it and see what's happening. So I would say ditch the number line test on that one. But if you fought through it, you know, it just would take a lot of mental, tangible thoughts. So, if you are the person that asked more questions than that, no biggie, just let me know if you can go back and take another look at some of those and see if the work on these couple of harder ones was helpful. And have a great night.